Welcome, Colonsay, and a discussion of the geology of Colonsay. Now, where is Colonsay? It's just north of Islay, a bit to the west of Jura, and you can get to it on the ferry from Kennaicraig via Port Ascaig, or more often from Oban to Colonsay, which goes about 5 times a week. Ferry from Port Ascaig gives you time.
There, you get 6 or 7 hours on the island. We've also stayed there a few times as well. So that's here's a little sort of Google Earth type shot of Colonsay. Colonsay, I mentioned, where the ferry comes in. It's got an island to the south called Colonsay. Some of you may have been there. It's very famous for its priory. I'll show you a picture of that in a minute. Linked to it by a tidal causeway. And the key locations we're going to visit today are highlighted there. Just as a bit of geography or post-social politics here. 135 people, just slightly less than Jura, which had 200. There's one owner, Baron Strathcona, lives in and the Colonsay estate is the main landowner on the island. Oronsay has 8 people who work for the RSPB, and the Colburn family use it, but the whole of Oronsay is an RSPB reserve. In fact, quite a lot of the island is operated by the RSPB. Quite a lot of presence on the island. This is Colonsay House. You can go around the gardens, around the house, around the gardens anyway. It's very nice. Just a bit of archaeology. This is a hill on Oronsay, but it's actually a late Mesolithic shell midden. The whole of that is limpet shells. So it looks like a limpet shell, and it is all limpet shells that are been eaten and used as fish bait by late Mesolithic people. And there's a lot of fish bones in it, and the debate is whether the people stayed all year round or whether they turned transitory. So, but I'm not a Mesolithic expert, so I'm not sure. But anyway, I did mention Oronsay Priory. This is allegedly Columba came here on his way from Ireland to Iona and stopped off here, but none of the remains here are of that age, obviously. This is probably 14th century, but there's a nice place to get to. You can walk to it from the ferry and cross the tidal causeway and back again to the ferry in time for a beer and a cup of tea or whatever in your day trip from Islay, but it's quite a long walk. But it's a lovely place to visit, very remote. And a lot of wildlife too. So as I say, the RSPB do quite a lot of work on the island, and it's mainly aimed at reserve and sustainable farming practices for the chough and the corncrakes. And there's some rare orchids. I think this is, if my notes are correct, Irish Lady's Tress orchid, which is incredibly rare, but it's found on Colonsay, and the RSPB sort of jealously guard it. So, some geology. Here's a geological map you've seen if you've been to my previous talks of the 3 islands, and you can see I said Jura last week was pretty simple geology. Looks from this map, it looks like Colonsay is even simpler. It's only got 2 colors, mostly green and a little red blob, and we're going to talk a lot about the little red blob in a minute and the green bit. You can see here, I've got a geological scale here. We'll talk more about them. This will become clearer as we go through, but there's a little blob of Rins complex in the top of the red, and then the rest of the green bit is called the Colonsay group, which is probably, and I'll be explaining a bit today why I think it's this part of the stratigraphy and the very early part of the Dalradian Grampian group. And then, but we think all of this stuff, this Beaumont sandstone and Colonsay group, which we get here on Islay and here on Colonsay, is slightly older than the main Dalradian sequence of Islay with the Port Ascaig tillites and the Bonhaven dolomite and the Jura quartz. I think this is older, but it's younger than the Rins complex. It's sort of stuck between the 2. So we'll talk a lot more about this and how it all fits together. Here's a geological column just to put it in the rocks on the column in a bit more detail. So we've got Rins complex at the bottom. There's high sort of mid-grade metamorphic complex, about 1.8 billion. The Colonsay group, 800 million roughly. But we're going to talk about that this evening, about why we think it might be 800. And last time we were looking at the Port Ascaig tillite and Bonnehaven Dolomites up in here, and then in the Jura quartzite we're up here at 700. So we're going to be down here and looking at this bit of the stratigraphy pretty much in isolation today, looking at this bit of the stratigraphy in the lower part of the Dalradian. Just about time, just as this is actually in time, and we're going to be looking at, this is the Colonsay group, we're going to be looking at around about 800 million years, sort of in the Neo-Proterozoic part of the Precambrian. And we're going to have a quick look at the Rinse complex down here, and there are some interesting rocks that are Silurian age, which we're going to come across towards the end of the talk. Okay. So that's time. I'll come back to time, make sure that you all understand where we are geologically in time, but we're going to be thinking about the late part of the Precambrian. Yeah. So here's a geological map of Colonsay, and as you remember, I had it all colored green. So virtually every color shading on this, apart from this little red sliver up here, and the odd bits of Silurian stuff, is all the Colonsay group. But it's divided into sort of different formations, as geologists do, purples and oranges and browns, sort of different mudstone, meta-mudstone and meta-sandstone. These are meta-sediments. They are sediments once upon a time, mainly sandstones and mudstones. And they occur in a sort of, you can see there's a sort of pattern here. Yeah. And they're all pretty much dipping this way, so that these are the older ones here. And if you go this, as you move from Colonsay this way, if you move from Colonsay this way, up this way, yeah, the rocks get pretty much younger and younger. So the Colonsay group is sort of at its oldest down in Oronsay and gets younger this way. So everything is pretty much dipping in this way. So the structure is relatively simple. And yet you can see that it's cut by these quite prominent faults, some of which have got sort of little lock-ons in them here. And there's a sort of picture of the sort of fault patterns in here. And we're going to talk about those because we're quite close to the Great Glen Fault. And a lot of these faults are parallel to the Great Glen Fault. And also, I believe, have some of the same motions on it that the Great Glen Fault has. So we're going to talk a little bit more about that during the talk. And I colored in red here because this is this little red sliver of the Rinse complex up in the far north east corner. Get my east and west wrong way around sometimes. So this is the northeast. We're going to have a look at that. So, and we're also going to look at some Silurian rocks, some Silurian volcanic rocks and igneous rocks that are colored in sort of covered in sort of basically covered in gray here. And we're going to examine these in some key localities. Yeah. So that's the sort of the geology, overall geology. And we're going to start up here, as I usually do, with the oldest stuff. It's a good way to start geology, is to start. I always have a problem when you're dealing with a sort of geology of a place like this. You start with the oldest, and you go to a place, but there's younger rocks there too. So you jump around a bit, which is what confuses people. But I'll try and keep the story going in a sort of geologically story-wise. But I will jump about if at a locality there is some interesting stuff. You always, as you would do when you're there, you would say, well, I'm not going to just look at that because it's out of sequence. You go and look at it anyway. So let's have a go to Balnahar Bay. This is the top end of Colonsay, beautiful beach. Lots of lovely beaches on Colonsay. It's from the, if you can take your car on the ferry, it costs a wee bit, but you can take it on a ferry, take your car to Colonsay, and then you can drive to Killoran Bay, which we'll come to later. And then it's about a 4-mile walk on a farm track to get to this bay. So it's not impossible to get to, and it is on a good track. But it is a wonderful place to come and visit to see what's going on. And it's just a nice place to get to, lovely day out. So here's a geological map. That photograph was taken from the headland at the south. Angus, are you moderating the chat? Some people, yeah? Just in case there's a question, maybe you could just chip in and tell me if there's something that someone's asking.
Yeah, absolutely fine. Yeah. That was just a general comment coming through.
Okay, if there's anything that you need me to stop and explain through the chat, just holler, will you? Okay, so yeah, the track from the parking area comes up here, and you can do this nice little walk here. This little red dotted line is my suggested walk. in volume 2 of my book, which is going to have this locality in it. And you can see there's some pink stuff, which I've said is Rins complex. And then there's some conglomerates, some meta sandstone, and some meta mudstone. So there's a bit of geology going on here, bit of interesting stuff. A lot of sand dunes, a lot of rabbits, but lovely place to come. Let's see what. So we're going to start here in the middle of the pink stuff. And here is the sort of bay. The previous picture of the bay was taken from up on the headland here. So this is the other side. And you start seeing actually some pink rocks. So they're pink on the geological map because a lot of them are quite pink. And so there's some, you can see some pinkish rocks sort of sticking out of the sand down here. But when you get there, there's quite a lot of grey rocks as well. And you can see these are quite interesting rocks. They've got grey and white bits in them, sort of folds here of these sort of white, light grey and dark grey layers. Some dark grey, light grey, and then some sort of quite light banding in here. Some other darker blobs and things like that. So these are all nice gneisses, but unlike the gneisses that we see that dominate the Rins complex and Isla, most of the gneiss here, I did say there was some pink stuff, but most of the actual gneiss is a sort of grey color, not a pink color. But there's some pinky bits, and the pinky bits here are actually a pegmatite. This is a coarse crystalline rock, ex-igneous rock that's been metamorphosed a bit, but it mainly alkali feldspar, potassium feldspar, giving it the pink color. And here's the gneiss, the gneiss, the grey gneiss here, yeah, and the pink sort of pegmatite sort of sneaking around and intruded in and folded into it, and it's a bit of a mess. You can see grey bits, pink bits all over the place. So quite difficult to sort of, you can follow the gneissos banding quite nicely in places. You can see there's obviously a gneissos foliation sort of running crudely through the outcrop here, through the exposure here, and then there's a sort of probably what was intruded later into the gneiss, and it must post-date the gneissos formation. This gneiss banding must have happened before this pegmatite was intruded. Anyway, there's been some dating done on this stuff, and also some geology of these rocks. And these things are, if you're familiar with the Isla rocks that we've looked at, they were cyanites. Well, these are not. These are granodiorites, which have got a lot of, which is basically a granite, but without much orthoclase feldspar. It's a granite dominated by plagioclase feldspar, granodiorite. So these are granodiorites originally. So they're meta-igneous rocks. They were once granodiorites, but they've been subjected to some gneissos metamorphism, and they've been dated. Now, you can get confused between giga years and MAs, millions of years, and giga years. So this is 1.89 giga annums, giga years, which is 1,890 million years, or nearly 1.9 billion years, are getting on to half the age of the Earth. If the Earth is 4 and a bit, this is nearly 2. So this is Paleoproterozoic age, 2 billion years, nearly 2 billion years old. So it's different rock to the Rins cyanites, and it's a different age. It's actually slightly older, and we'll come on to that, a bit more about that in a minute. We also dated the pegmatite, and the pegmatite, surprise, surprise, is younger. In fact, I would have been astonished if it was older, because it looks like from the field relations that it is actually intruded into it and doesn't contain the gneissos foliation. So this gneiss must have been a granodiorite, igneous rock. It was turned into a gneiss, and then not long after it, the pegmatite was intruded after the gneiss event. So you've got quite a lot of geology going on here in this small little outcrop, quite a lot of interesting geology. They're dated because these rocks contain some zircon, and we're going to talk a little bit more about zircon in many contexts this evening. Zircon is an accessory mineral in these things. The zircon crystal, and I'll talk a bit more, so don't hold your wish if you don't understand it at the moment. The zircon crystals contain minute amounts of uranium in their crystal lattice, and uranium, as you know, is a radioactive material, decays to lead, and you can measure the quantities of the uranium and the lead and work out an age. So these are uranium lead dated rocks using zircon in the granodiorite. So where else do you find these things? Yeah, I mentioned Isla. And there's some sort of, a lot of these sort of pinkish rocks up here in the Lewisian, which is this sort of dark purple here, and they're often pink rocks. And originally, before this dating was ever done on the Colonsay and the Isla rocks, everyone assumed that this Rins rock in Isla and in Colonsay was just another bit of the Lewisian. Why wouldn't it be? But it's separated by the Great Glen Fault, which comes screaming down through here. And the geology of this bit of Scotland, as Angus has probably pointed out to you many times, is very different to the geology across the other side of the Great Glen Fault, because this bit was miles away, maybe 700 miles away at the time. So, so there's a great big dislocation along the Great Glen Fault system, which runs very close to Colonsay. And then the question is, does it come through here, the Great Glen Fault, and go down here and into Ireland, or does it go out to sea and just remain out in the subsea area here? And so is the Rins complex part of the Lewisian, or is it not? And so until we got the dating done, we didn't really know that. We just sort of, and all the old mappers in the old survey just called it Lewisian. And it was Lewisian until about 1990, when the first dating was done on Isla Colonsay. So I just thought I'd just throw in a couple of nearby pinky rocks to show you what's going on. So those of you who've been to Isla with me on virtually and for real who've been to Losset Bay on Isla, where you get pink rocks and sort of greeny grey rocks. And this is a cyanitic gneiss, 1.8. And then there was so this gneiss was a syenite. Then it was formed into a gneiss. And then like the ones on at Balnahard, there was an intrusion of later things, including pegmatites, which are undated here on Isla. And then we know that all of that lot was metamorphosed at 1.7. Yeah, so we've got all these dates flying around. All makes sense in a minute. And on Iona, we've got pink rocks and grey rocks as well. But a lot of this stuff is actually 2.7. It says CA, it means GA. Yeah, and that's been metamorphosed at 1.8, 1.9, and it has a deformation at 1.7. So there's lots of things happening in Iona and Isla and Colonsay. And let's see if it makes any more sense. Just wanted to show you this picture. I'm not going into details of petrography, but this is one of these diagrams where you can put igneous rocks on a plot. And this is plotting silica against alkali, i.e. sodium and potassium. Yeah. Now a syenite that we've seen at Isla is quite high in alkalis. It's quite high in sodium and potassium. In fact, quite a lot of potassium in the syenite, and it's quite low in silica because it doesn't even have any quartz in it. It has no free quartz in it. So syenites plot up here in this diagram, and the Isla syenitic gneiss plots here, which is why it's called a syenite. Syenitic gneiss. It was a syenite. It's now a gneiss. The Colonsay gneiss that we've just been looking at, the grey stuff, plots down here, and it has much lower potassium and much higher and higher silicon. So it's more like it is a granodiorite. So it's a very different rock, and we've seen it's got some sort of different ages in its deformation as well. How do they form? Well, we do believe that all these rocks, the alkali rocks are formed in an island arc, deep in an island arc, where an oceanic crust plunges underneath its own oceanic crust. As it goes down, it induces partial melting in the mantle, and this melting of the mantle, not of the plate itself. The plate's cold, but the water in it that does tend to melt the mantle by the addition of the water and the wet sediments that go in there. And you can get a whole variety of rocks in here. You can get ones that are straight melts of the mantle originally, and then they can, as the subduction process comes on, those melts can get melted, and you get sort of an evolution of the rocks in here. This is what's going on underneath. This is the Leeward Islands, Windward Islands in the Caribbean, underneath the Caribbean plate, where the Atlantic plate is going underneath the Caribbean plate. Is exactly this sort of picture. But we're looking at rocks that were probably formed 50, 60, 70 kilometers below an island arc in a sort of with melting and then sort of intrusion into the crust underneath volcanoes at that time. So what we actually believe and there's been some geochemistry done on it, that these orthogneisses, they call orthogneisses the term that's used because it's derived from an igneous rock. It's actually first melt of the mantle, and it's known as juvenile crust. This is work done on rare earth, hafnium and neodymium isotope work. But we know at 1890 this is first melt of the mantle coming up into underneath the island arc. All the other stuff, and we see these rocks in some places like the Stanton Banks offshore in the Rockall and in Northern Ireland, or northern part of Ireland, the Anargis ice complex, are all slightly later. Yeah, they're 1.8 billion, not 1.9, nearly 1.9. So Colonsay is unique. It's the only place where we've actually got true early crust forming at this time. Everything else is a bit younger, and it could be that it's melted from this stuff. It's reworked, it's melted from this. So this is the original stuff. The Isla stuff is slightly younger and is derived from it. The whole of this island arc was, there's Isla Colonsay area here on the volcanic arc, and this is the continent known as the ancient supercontinent known as Columbia, or Nuna, sometimes called Nuna if you read the literature. So 1.8 billion years ago, roughly, there was an island arc like the one we saw in the picture there. Offshore here, there was a subduction zone, probably going this way. Here's northern Scotland. This is the Louisian Archean basement of Columbia. This is the northern part of Rockall. This is Greenland. This is the Baltic Shield. And this is Isla and Colonsay trundling into and eventually going to collide in here. But we've got a volcanic arc forming, and all these calc-alkali rocks are being developed. And then 1.7 billion years ago, the whole lot slams into Columbia, and there's an orogeny, and there's metamorphism. And then we've now got a bit of Scotland, northern Scotland and central Scotland sort of joined together, the Grampian, and southern Rockall and Greenland, southern Greenland, and a whole load of stuff in the Trans-Scandinavian igneous belt are all the same rocks. Yeah, they're all the same rocks with this same sort of history of 1.8, 1.9 billion years formation and 1.7 billion years metamorphism. And the metamorphism has affected the Louisian, and it's known in Louisian geology terms as the late Laxfordian, around about 1.7 billion, 1,700 million years ago. So quite a nice little story here, but Colonsay is unique. That's what I wanted to point out. You don't need to follow this whole story about this thing and all the isotope work and the stuff, but nevertheless, it's very juvenile, young crust. It's very juvenile, first melt crust that was formed, and it's unique. And it probably underlies, before I go into this, it probably underlies the whole of, we're just so lucky to see it. If you went underneath the whole of Scotland from Isla to Peterhead and drilled a hole, you would find Rins complex. You'd probably find Rins complex rocks of all these different ages. There'll be pods and pockets of the old stuff, the 1.9 and the 1.8, with all this 1.7 stuff. So an interesting bit of it, and we're just seeing little windows, little just slivers of what's underneath the roots of Scotland in Isla and Colonsay. And Colonsay is very unique because it is that one place we see the very old stuff. There's probably a lot more of it underneath. If you go to southern Greenland, there's a ton of this stuff, yeah, because there's fantastic exposure. If we had more exposure, we would learn a lot more. So let's have a look at the Colonsay group, which is the bit that's sort of above it, yeah. So we're going to go back to, we're still at Balnahard Bay. We've had a good pot around all our orthogneisses and pegmatites in the pinky bit. So we're going to go up here where you can see we've got an orange strip here marked as a conglomerate. And we're going to go to this little hill over on the north side of the bay called Lake Buie and have a look at that. And what we find is a conglomerate, and it's right next to the gneiss, and everyone originally thought, it's a basal conglomerate. This is the youngest set. These are the sediments, the sort of oldest sediments that sit in what's called the cover over the basement. You can use the word cover and basement. So the basement is the Rins complex, and this is the cover sequence of metasediment, now metamorphosed sediment rocks that cover the basement. So then you look at these pebbles, and they're actually all quartz and quartzite. There's no gneiss or pegmatite or any other funny metamorphic rocks. These are nothing like the pebbles in the basement. So this is not a basal conglomerate at all, because it's not related to the basement. It's not pebbles of the basement caught up in the first sediments, which is what you'd expect if you were covering up a basement thing. So these are strange conglomeratic beds, but next to the gneiss. In fact, that's the gneiss there. That's a sort of the grey gneiss in this outcrop here. And this is a sort of, there's a bit, this is the pebbly sandstone. There's a pebble. You can see a pebble there, pebbles here, pebble there. So there's pebbles in this sandstone, and there's a sort of metamudstone, siltstony type unit that's sheared to hell, and it's full of quartz veining. So there's a bit of deformation going on here, and this is probably where I've drawn the fault. There's a fault between the gneiss and this stuff. Yeah. So they're not really geologically related. They're just faulted against each other, and there's probably a lot of shearing going on in here. But the actual fault plane is very difficult to see in all the grass and the sand dunes in here. It's quite difficult. You can map it, but it's very difficult to observe it. But this shearing is part of it, so maybe it is a 3 or 4 meter wide sort of sheared zone between the sort of grey gneisses and the meta sediments above it. You go on the other side of the bay, you get some more meta mudstones. Some of these are quite folded, and these sort of quite nice sort of chevron folds on the other side. And this is meta mudstones on the south side of the bay. And while we're here, we jump around a bit, but there's a beautiful, beautiful intrusion here. Can you see this? This is the meta mudstones here, cut by this intrusion here. And you can see here, this is a sort of dike, an inclined dike of this sort of grey-brown rock. And it's got coarser stuff in the middle and finer stuff on the edge of it. This is a lamprifier. We'll come on to that when we come to Colonsay Bay, but just want to remember, this is a lovely picture of a sort of a chilled, margined dike intrusion of a lamprifier, which is a potassium-rich, weird sort of rock, intermediate rock, which we'll come on to it later, but they are intruded into this and are significantly younger than this deformation. So if this deformation, whatever age this deformation was, and it's assumed at the moment, and I'll come on to the reasons why I think it is, if this is the Grampian deformation in the Caledonian orogeny of 470 in the Ordovician, this must post-date that. And there's been some dating done on this to show that it is actually younger than this, which is what you'd expect from the field relations. If that was what I saw in the field, I would say that intrusion of igneous rock has got to be younger than this, than the deposition and the metamorphism of this metamudstone unit. And around the corner, it's even more deformed. Here, I showed you the kink folds and the chevron folds. Up here, you've got these weird, this is not my picture because I didn't get around this corner here, but I'm going to go back and look at it. I think this is actually sedimentary fold slumping that's actually been folded as well by the fold, but I think there's actually some really weird folding going on in here. It looks like it's a mixture of tectonic and sedimentary slumping. And I'll come on to a little bit more about how all that picture fits together, but lovely picture from the BGS of some beautiful, I need to get to this place. It's quite difficult to get to, but I need to get there. Take my own picture. Okay, we're going to go south. I think I've got a map coming up, but this is the sort of typical scenery of the sort of west coast of Colonsay, sort of halfway down the west coast of Colonsay, looking along strike of the beds towards the northeast. This is a place called Macrans, and this is a golf course, 18-hole golf course. On the Macca, the only thing that's manicured on it is the greens. The rest of the fairways and everything else is left to the rabbits and the sheep and the little airstrip in here as well. So we're going to, this is looking south from this from the hill I'm standing on towards Oronsay. This is Dun Oronsay here. This is the Oronsay Priory is in here, and in the far background is Isla. So we're looking. So this is looking down the strike of the Colonsay group towards Isla. Let's see where we are geologically. So we've been up here, yeah, and we were now here, and some of these this is called the Dungallan grit, and there's the Macran sandstone unit here. So these are some sandstone units which form quite the prominent sort of high ground here and here. And then the mudstones are the purpley colors, which tend to be the lower ground, tend to be lower relief. And there's our fault pattern that I showed you before. And there's the thing, and there's the volcanic, and this is where we are now. So we're now here at Dungallen. Those views were taken up that way and down that way. So we're in the central part of the island here. And here's a wee map. So you can park your car here and you walk down onto the golf course, and you can walk to this little beach here. There's Dungallen itself. You walk back over the airfield through a lovely pass called Turnagal onto some dunes, and we see some rocks at the far end. So we're going to just do this little walk just very quickly. It's not a complete field excursion, but we'll just dot around on this little walk just to get a flavour of some of the geology of the Colonsay group. And you can see I've got different colours here. Then we'll have a look, see what they look like. So the first things we see is some meta-mudstones with quite a slaty cleavage, quite a prominent slaty cleavage developed in these meta-mudstones, and some meta-sandstones forming this little ridge here. Yeah, and here's the sort of, so we get meta-sandstones and meta-mudstones. Quite thick sandstones units. And in the sandstone, you often find cross-bedding. This is quite coarse. I haven't got a scale here, but naughty geologists should always put a scale on a photograph. It's probably cropped. I've cropped it, but took the scale out of it. There should be a hammer or a walking pole or something in it, or a magnifying glass, or lens cap, in the days when you had lens caps. So yeah, but you can see this cross-bedding here. So there's obviously water currents here, truncating these here. So if you had to look at this rock, you would know that is younging that way. This is truncated by this, and this is asymptotically curving to the base. So you know that this, you can work out which way up that has got to be the top of the sequence. So it helps in these sort of rocks to work out. These things are very good for helping you get the structure right. You get some quite gravelly. This is the Dungallen grit, and it's grit because it's got this very gritty layers in it, some more sandy units, and then some gravelly beds as well. Yeah. Quite a lot of the interpretation of this is that it is probably some sort of fluviatile river deposits of some sort. Yeah. River currents forming these gravel bank bars, channels, all sorts of things. There are some nice channels. Here's a channel. Yeah, you can see this. This looks like it's cut across through here. Looks like it's sort of some sort of channel system in here, and then truncated by this unit here, which has got some cross bedding in it. So this is the Dungallen grit. So quite a nice sort of, you can see a lot of sedimentary features in it. My point is that it's not all metamorphic. The metamorphic grade is quite low. This is only greenschist facies biotite zone at the highest. So a lot of the original sedimentary features have been preserved. You can see here, this is not a horribly deformed, messed up sequence. What you do, where you just get a thick mudstone unit, so that's what we saw, remember, at Calor and up at Balnahar, where we have thick mudstone units, you get some deformation. And then you get sort of things like this is possibly some soft sediment deformation. Remember, I taught the soft deformation folds. There's certainly things going on in here with things pinching and swelling, and maybe sand bodies moving about. If they're in a sort of fluviatile system, and there's some argument that some of it might be deltaic, with some very, very high deposition rates, you would expect to get a lot of soft sediment deformation going on, with sand being dumped onto mud very quickly, a lot of dewatering structures, a lot of movement of fluids as the thing compacts. And so you do get a lot of sediment, and then you get, I just pointed out earlier, possibly some slumping as well, like that. So you're getting a lot of movement of the rocks before you get any metamorphism. So the problem is, if you've got a deformed sedimentary sequence, a lot of sedimentary deformation in it, already got folds and thin bits and intrusions and dikes and things, then you metamorphose it. You're trying to work out how many metamorphic events have you got, and you might get a bit muddled up between a sedimentary event that's been metamorphosed or an original flat-bedded rock that's been metamorphosed and folded. So it can be quite complicated, and structural geologists have to be very careful that they're not actually looking at sedimentary features that have been folded. This is as you walk south, you get some of these thick sand units. Some of these, as mentioned about deltas, some of these sands are properly delta top sands, tops of big channels and delta tops. This is one of these faults. Remember I showed you the faults all trending from northeast to southwest across the island that were like the Great Glen Fault. So this is one of these faults as it comes out onto the coast, and it's got a lot of broken up rock in it here. And the reason it's got broken up rock because there's been a lot of movement on these faults. And the glaciers and the streams have eroded out them, and as you say, we've got chains of little lock-ins along these fault plains. So this is the fault as it comes to one of these faults as it comes to the coast. And at the far end of the walk, we end up looking down over to Orange. This is Oronsay in the background here, and you get some sort of interbedded sort of thin sands and muds here. And this is the part of it, what's called the Oronsay Greywacke sequence, and these thin beds of sand, as you go further in the sequence, get more and more thick sands. And those of you who've been to Isla, to Salago Bay, we believe that this part of the sequence here is actually pretty similar to what we're seeing on Isla. We'll talk about the correlation between Isla and Colonsay a bit more. I've got a diagram coming up. There's a bit of deformation. You can see that there's something going on here, but there's obviously some sort of feature in here that's cutting right through here, and there's some deformation on the sort of low angle thrust that's caused a bit of just a small little thrust, but it's caused a bit of buckling, and very classic fold at this level, at this scale of these little what we call an asymmetric fold. This limb is quite shallow, not dipping very steeply, and then you get this very, very steep limb on this side of the fold, and it's cut out, and it's cut by these faults, which have now got some quartz in it, because when you create this push and fluids are moving up the fault plane, you get a little hole developed here, and the quartz tends to then freeze out into these the quartz rich fluids that are flowing through, and you get these sort of little knots and pods of quartz in the sort of cores of the anticlines. And it's also following the little thrust planes as well. So it's quite a nice little example. And often structural geologists will look at small folds and say, well, that's just mimicking the big fold. The bigger folds are this type of structure. And in fact, this is pretty typical for a lot of the Dalradian of Isla and Jura and Colonsay, is that you get these asymmetric folds, and the transport direction is this way. The pushes come this way. And a lot of so this fold is verging to the northwest. It's been pushed from the southeast and is verging that way, going that way. So the tectonic transport direction this way. This is a small example. You can see it's just on the beach. It's only a meter or so thick, but it's a good example of what's happening on a larger scale as well. At least you can see it here in a lovely little outcrop. Then you get some other ones, more folds here. And again, whether this has originally had some soft sediment deformation that's then been accentuated by the folding, because some of these top layers haven't got much. It's got a little bit of a fold in it, and there's a cleavage in it. There's a cleavage that's sort of axial planar to the sort of deformation of this asymmetric fold. But whether this unit was originally a plain bed or not, I doubt. It probably was a sort of some soft sedimentary deformation had gone on, some thinning and thickening, and some dike intrusion possibly, and then it was folded because it already was a sort of uneven bed, and it would have picked up the fold. So I think we're getting a combination of sedimentary and tectonic folding here. You can see this there's obviously a plane coming through here as well, and it's developing this cleavage at this level. So nice little coastal examples of some structural geology. Another one with asymmetric fold. You can see there's obviously a plane of weakness coming here. You can see the fault plane here. A lot of folds are cored by faults. So this is definitely a fault cored fold, asymmetric. You've got this steep limb here on the sort of verging to the northwest again. Lovely little example. So how are we doing? Let's see how we're doing for time. All right, okay, not too bad. So here's the geological map again. So we were over here looking at this stuff here. There's the faults. There's the Colonsay gneiss again. There's the stuff we're going to look at next. And we're going to go here. We're going to go to Colorham Bay and have a look at these. There's this grey stuff here, which I alluded to earlier about the lamprifiers and a possible later stage age. And we're going to look at this. There's also, you can see here, the structure here. There's a sort of like a circular outcrop. Yeah, you see that? So this is what's known as the Colonsay Bay syncline. So we're going to look at this Colonsay Bay syncline. We're going to look at some rocks on the south side, which are coloured blue. And often when it's blue, it's limestone. That tends to be what happens in geological mapping. And then we'll look at these igneous rocks, some igneous rocks in the core of the syncline here. So here's one of my pretty maps. You can drive to here from the ferry if you have your car, or you can walk. It's about a 3-mile walk from the ferry if you're walking or cycling. And this is where you park to go to Balnahard, to the bay. So you can park here or here and then take this track. You can cycle this. You can't cycle that hill. That hill's really dead steep, but you can walk or cycle. I've cycled a couple of times out to Balnahard along this track. It's cyclable all the way, apart from the steep hill. But we're first of all going to have a look at the south sort of west side, where I've coloured in some blue limestone as a hint, and then we're going to cross the bay and have a look at these igneous rocks over here, which I've mentioned here, syenites, hornblendites, and explosion breccia. So I'll come on to that, but I'm going to look at these metasediments here, which are the sort of some of the youngest part of the Colonsay group on Colonsay, and it's the youngest bits we see of the whole Colonsay group. Remember, it's got younger as we've gone from southwest to northeast. So we're up in the northeast. We're in the sort of younger part of the Colonsay group sequence here, and we're going to be looking at this bit. And here we have what's known as the Colonsay limestone. It's a sort of bedded, brownish structure. It's just thin beds. You do get this sort of weird bedding here, which reminds me of the Bonnehaven dolomite, sort of possibly shallow water, tidal storms. Yeah, about the only place I've seen any structure. There's a little fold here, another asymmetric fold structures in here. Yeah, you see that just kicking through here? Just a little tiny little fold in it. But this, you can see them coming up through here as well. It's beautiful. But most of the time it's fairly well bedded and pretty structureless. But there is this bed of limestone, several beds of limestone on the south side of the bay. It's the only limestone really we see in the Colonsay group. In Isla, it's deltaic and fluviatile sandstones going up into turbidites. On Colonsay, it starts off with turbidites and ends up in deltaics and fluviatiles. And but at the top of the sequence, we get these sort of limestones developing. We also get some strange folds. This is a little metamudstone below the limestone, and we get these things called sheath folds, which are these very, very, very tight, curved, tight little folds. Yeah. And they're really difficult to trace. You can trace some of the beds around a little bit, but they're very, 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 very distorted here like this. Yeah. So we'll come back to sheath folds in a minute, because I'm going to talk about this slide comes up again a bit later, because I want to talk a bit more about what they're doing. But I just wanted to just show you a nice picture of some of these sort of tight folds in below the limestone, but it's a sort of interbedded sort of laminated siltstone with a few thin sandstones that's been deformed in this sort of strange way. Okay, I kept alluding to the correlation of the Isla and Colonsay. So just to go back to, this is what we see on Colonsay, the Oronsay Greywacke. We didn't go much below, when we looked at that picture of it, we didn't go on to Oronsay with this, because I've been to Oronsay, but I only got to see the priory. I haven't actually seen the rocks on Oronsay, so it's a thing for another day. But the Oronsay Greywacke, we don't see the base of it. It's all here. This is all the turbidite sands. Then it's mudstones. Then the Dungallen grit. You saw the channels and the gravels and all that sort of good stuff. And the Macrins Arcos, which we didn't see yet. And then we're up here at the top with the Colonsay limestone. So we've got this sequence here, and it's believed that this is turbidites. This is fluviatile, river deposits, shallow marine, some more fluviatiles, deltaic stuff, shallow marine, and the Colonsay limestone. So we're sort of shallowing up sequence here. Yeah. On Isla, we get the opposite. We get shallow rocks at the bottom, deltaic and fluviatile things at Kilheran and the cool grit, and then onto the stuff at Saligo, which is the Greywackies. And we think that some of these Greywacke sequences on the northern part of Isla correlate. That's the geological term for correlate. They are the same rocks, just 40 kilometers or so apart, but they're the same sort of rocks. And up here in Balnahad, where we started, we get the conglomerate on the Rins, yeah. But it looks like probably this conglomerate geologically is about here, yeah. It's up here somewhere, yeah. So we're seeing quite a lot of missing stratigraphy in this. So there's a sheared contact I showed you in some of those early photographs between the Rins complex, between those grey orthogneisses and the pebbly quartzite conglomerate, which are unrelated to that. Down in Isla, especially down on the Rins, southeast Rins, and I haven't really shown you, there are conglomerates there that have pebbles of Rins in it. There's a breccia down in Isla that is definitely derived from the Rins. We've actually taken some zircons from it, or I haven't personally, but it's been done. And that is definitely almost certainly a basal conglomerate to the Colonsay group on Isla. So this conglomerate here is a true basal conglomerate on Isla. In Colonsay, it's not. It's just circumstance. It's just an accident that we've got this little fault sliver of stuff. Okay. Just thought that this is just. I was going to try and get more seabed topography maps out for you, but I ran out of time. It take wee time to download. Just to show you, this is Isla, where the Colonsay group is here, and this is the fault. This is the fault you can see on the seabed quite nicely. It's a Grignard fault, yeah, which separates the Colonsay group on Isla and Colonsay from the main Dalradian of Isla and Jura. So there's actually, you can see that it actually comes out on the seabed quite nicely here, and it's and here's the Great Glen fault up to the north here, yeah. So Colonsay is sort of triangular sandwich between the Great Glen fault and this Grignard fault, and the argument runs that this is actually a splay of the Great Glen fault. There's sort of the thing is split and splayed into sort of several sections, and all the little faults I showed you running through Colonsay at this sort of angle are probably splays off this fault. Yeah, so this is sort of splayed out as well, and this certainly has a lot of strike slip sinistral component. It's gone to the left, and this probably has as well. The Grignard and all the faults on Colonsay seem to have gone to the left as well. So. So we were looking at, we've looked down here, we've been here in the timeline of the Colonsay group 800. I'm going to look at that in a minute. We'll just have a quick look at the Silurian rocks that we see at Killoran Bay, and then we're going to have a quick discussion at the end as to why we think these Colonsay group rocks are the age we think they are. That's the sort of format of the last bit of the talk. So this is the slide, this is the bit, pretty much the slide I showed at the very introduction, the north side of Killoran Bay. So the limestones that we were looking at were over here. This is the limestone section. On the south side of the bay, this is looking south. Nice raised terrace here. This is the main rock platform. Those that want to, but I'm not going to talk glacial stuff today. And there's some rocks here marked with an X, a boundary here, so S, the S, and H. And you saw my geological map earlier, and I had an explosion breccia, so that's an X for the explosion breccia, S for a syenite, and H for a hornblendite. Let's go and have a look at these three major rock types on the beach. It's a lovely walk. This is the best bit of geology, the best bit of accessible geology on the island, because you can drive to it or walk to it or cycle to it from the ferry, and it's fantastic because you see this stuff. Yeah, this is the explosion breccia. It's just packed with bits of bedrock, yeah, of the cleaved and bedded meta-sandstones and meta-siltstones of the Colonsay group, all jumbled up together, and a great big piece. This is a great big fragment of meta-mudstone here. Yeah, so and you look at it in detail. This is the breccia is just, there's very little matrix and little pockets of little sort of glass in places, but all this stuff is just sandwiched together. And we believe it was formed by fast rising gas in a vent, underneath a volcano. But its gas streaming has just broken up the bedrock and brought it all up and choked itself. And it's just, so these must have been very violent as well. They are known as explosion breccias. It must have been a pretty horrific sort of time to be around. So this is the explosion breccia. Come back to it in a minute because I've got another picture of it. Then we get cyanite. This is a pink cyanite, unmetamorphed. This is not a meta-cyanite or a cyanitic gneiss or anything like that. This is a cyanite, alkali feldspar, and some mainly alkali feldspar, a little quartz, very little quartz in it, and a few bits of biotite and amphibole in it, but not a lot else in it. Quite a compact sort of rock. This grey rock at the bottom I'll talk about in a minute. Some of it's quite dark. It's often pinkish and lightish colour, but when you get a bit more mafic minerals in it, you get a darker rock here. There's some funny rocks in the foreground, which we're going to look at in a minute. There's some funny rocks in the background as well. But the cyanite is not all uniform. It does have a sort of some sort of gradational bits, and some pink bits and pink bits and then dark bits. But this is just a change in the number of, in the sort of mafic content. There's much more amphibole and biotite in this bit than there is in this bit. At the far end of the bay, you get this thing here, which is sort of dark, sort of looks a bit gabbroic, dolerite type color, with chunks of quartzite in it. And this is entirely, virtually entirely amphibole. This is known as a hornblendite. It's an entirely hornblende with a tiny bit of feldspar in it, and great lumps of quartzite in it. So this has got, you know, in places the quartzite packs the whole thing, and you get a bit of hornblendite and lots of quartzite pebbles. So this is like another type of explosion breccia, but it's got different content. This is all quartzite, whereas the other one had a lot of banded siltstone, metasiltstones in it and stuff. So there's some really strange rocks. And then the hornblende sometimes comes into the cyanite, so it tells you that the hornblende is later than the cyanite. Yes, this is the hornblendite and this is the cyanite. And this is a lamprifier, which is younger again, which cuts across the two. So these are all very strange, highly potassic rocks, all part of the apennite suite. People have heard of appenites, I guess. They're very common in this part of Scotland, with these strange, very high alkali rocks, lots of potassium minerals in them. So a lot of biotite, a lot of potassium amphibole, a lot of potassium feldspar. The pink feldspar is potassium feldspar. So these are highly alkali, highly potassic rocks. And this is the lamprifier that cuts through the explosion breccia. Yeah, it's quite a thick one, this one. It's a couple of meters, maybe more, 2.5 meters thick. And this is all explosion breccia here with all the, yeah, so we can know that we think that the cyanite this is the first thing, then the cyanite, then the hornblendite, and then the lamprifier. So we have a sort of sequence of igneous intrusions in this little area here. And on the beach, there's a lovely, like I showed you at Balnahard, a lovely one of these sort of chilled margin lamprifiers with the coarser grained center to it in the meta sediments here. Cuts a little bit. It's almost concordant with the bedding. In fact, in this place, it's almost so it's almost a sill. It's come up almost parallel with the bedding here. And in places, the lamprifier sort of, you can see it sort of it sort of gets in and around the cyanite as well. It sort of wraps itself around bits of the cyanite. So it's a quite sort of invasive rock, but it's sort of got very regular sort of boundaries in places. And that's Colonsay, which I didn't get a picture of. I meant to get a picture. Colonsay Bay, there's another one of these things here with another breccia, explosion breccia here up behind the hotel. So there's the pub here. If you're spending time resting at the end at the ferry, you can go and pick up some of this. It's almost a diorite. It's much more. It's more like the darker part of the cyanite. It's got. It's a more intermediate rock with sort of some a bit of plagioclase feldspar in it as well. It's a beautiful rock. Sometimes diorite. Sometimes no salt and pepper rock. It looks like a mixture of salt and pepper, sort of white bits and black bits, spotty stuff. This got a lot of biotite in it as well, and some of the pink feldspar. It's a lovely rock. And I just looking at my photograph. I hadn't got a photograph of it. I've got specimens of it sitting in Islay, but I'm not in Islay and I can't get to Islay, get specimens. So if I was in Islay, I'd just take a nice photograph of the rock. Anyway, I'm not going to go into the details of how lamprifiers and appenites are formed, but there's a model that's known as slab breakoff, where there's a sort of you get contaminated lithosphere coming up underneath a slab like this, and this is a mechanism that's been researched a bit for getting these very, very strange alkali lavas, intrusion, reservoir, all sorts of, I mean, people have done a lot of work on this stuff, but the appenites are a complicated group of very interesting rocks. But they're believed to be quite late on in the orogenic process, and I haven't got to this stage yet, and they believe that they're probably intruded along the fault lines of the Great Glen Fault. I'll come on to summarize that in a minute, because I wanted to just quickly talk about the age of the Colonsay group before we finish. How old is the Colonsay group? It hasn't got any fossils, and it hasn't got any datable rocks or minerals. Remember, we talked about the gneiss having zircons in them. These Colonsay group rocks have zircons in them, but they're detrital. They're derived. They're sandstone. They're in the sandstones. They're derived from the igneous rocks they were eroded from. So we know there are no fossils in them. We know they must be older than the Cambrian, and we know they must be younger than 1.8 billion because they don't have the amphibolite facies metamorphism of the gneisses. So we know they must sit between they must be late Precambrian, younger than this and older than that. And how does it fit the rest of Scotland? So there's the Colonsay group on Isla and Colonsay, sandwiched between these sort of the Great Gunyard Fault and the Great Glen Fault. And what does it relate to? Does it relate to the Torridonian, which has often been related to, or some people think it looks like the Torridonian of northwest Scotland? Is it the Moyne, that's the pink stuff here? Is it related to that? Or is it the Dalradian, which is all the yellow stuff here? And I've divided the yellow Dalradian into three bits. The Darver-Bancor group, which has got two deformations, as has the Moyne. The Grampian group of the lower part of the Dalradian, which only has one deformation, or is it part of the Appin group? So which bit of this geology, is it the brown, pink, yellow, green, or orange? We don't know. Well, we have an idea, and this is what I'm just going to go through in the last few minutes of the talk, just to go through which of these it might be. Now, it's been believed for a long time that the Colonsay group has two deformations, sort of early and the late. Like the early survey, they always thought there was two deformations, which when you read the literature, it means this thing and this thing, which is related to the Great Glen Fault movements, and this thing, which is the Grampian event. So this was the two events that were talked about in the early literature. But other geologists have been since and saying, well, there's these sheath folds here, and there's some shearing here. Maybe you've got a D1, a D2, a D3, and a D4, 4 phases of deformation, and an early one and a late one. So if you've got an early one and a late one, that's like the Moyne or the Glen Bancor or Darver group. That has two deformations. So that might tell you that it's, if Colonsay group has two deformations, it relates it to those sequences, not to the Grampian group of the central part of the Highlands of Scotland, which only has one deformation. This one, yeah, doesn't have these early ones. But the question is, are these early ones really that early? And are they really, if they are there, but are they actually all part of this? Yeah. Are they all part of the early part of that? And some of these faults that have been moving, these shear faults here, may have been extensional faults when the rocks have been deposited. Then there may have been thrust faults, become thrust faults later, and then become strike slip faults even later. So some of the, no wonder you're getting tons of stuff, and you've got sedimentary deformation anyway. So it's a bit of a mess, but interesting nevertheless to try and unravel it. And it depends where you come from, which you believe. Yeah, I tend to believe that we've only got one event here, but there's been some sedimentary deformation and there's some shearing near these faults. Yeah, and I tend to think we've got one event with a later folding related to the Great Glen Fault movements. And that's what you see here. You can see these things are offset. This bed of sand here. It's offset from this one. Yeah, these are off. This is offset here, and it's all offset synastry. You can see the movements I put on here. And this Caloran-based syncline may be related to maybe an interference figure, maybe an earlier fold that's then been folded again by in between these strike slip faults. This is probably a strike slip fault as well running down here. So all these are little splays with small displacements. Unlike the Great Glen faults, hundreds of kilometers, this has only got half a kilometer, maybe a quarter of a kilometer of movement. But there's certainly a lot of strike slip faulting going on, and which is affecting it. So that the old geologists that went there in the sort of the survey geologists at the beginning of the 20th century were there. They saw two phases, saw the Grampian phase, and they saw this phase, which is related to the volcanics. And so you've got the Grampian phase 470 and this at 430 Silurian. So you've got two phases of deformation, but they're not anything older than that, in my view. We just quick look at zircon data. I'm running out of time, so I'm going to have to rush through this very quickly. Zircon, gem mineral, obviously, lots of uranium in it, decays to lead. Also use titanite as well because they both got uranium in the crystal lattice. Yeah, and these are the sort of detrital zircons that you find in a lot of these rocks here. The youngest, when I say detrital, it means they're derived. So you can look at a rock with a sedimentary rock with zircons in it and say, well, look at the age of the zircons in it and look for the youngest one you can find that tells you the rock, the deposit must be at least that old or younger. Yeah. Yeah. Because it can't be it can't be older than that because it's got one. So the youngest detrital zircon in the Colonsay group is 1 billion years old in the Killoran flags up at Killoran. And there's a detrital titanite lower down in the Dungallan grit that we saw, the little pebbly grits we saw, that's 940. So the group must now be between 940 and 470. We know the Grampian deformations are 470, so it must be sandwiched between these two. And this is going to take too long, so I'm not going to go into it, but what you do is you draw your profile. What people do is draw the profiles up of all the distributions of all the zircons in it, and they compare them with other geology sequences. So they compare them with parts of the Torridonian. You get these sequences here. This is age. So the Torridon group in the Torridonian has Archean grains, some Paleoproterozoic grains, and some Mesoproterozoic. So you've got a sort of profile of grains, ages in these geological sequences, and they're quite different. You can use this differences to try and help you correlate. So the Sleep group and the Torridon group are quite different. They don't have any Archean grains in this bit. These ones do. This is on the Stur group at the base of the Torridon is entirely Archean group grains. This is the Moyne. But what distinguishes the Moyne is that very, very little Archean. So the Archean Lewisian gneisses weren't exposed in the Moyne, even though it probably sits quite close to it. There was very few Archean grains in the Moyne. The Dalradian, the lower part of the Dalradian, has no Archean grains at all either. This is the Grampian group and the Dava Banker sequences down here. But the upper part of the Dalradian, the main part of the Dalradian, the Appin, the Argyll group, and the Southern group, a lot of Archean grains in here. So this has been the Archean, the Lewisian type rocks have been exposed, and they're in the Dalradian. Yeah. So what does the Colonsay group look like? Well, I'm going to look at the explosion of this bit here, and there's parts of the Grampian group that look like this. Too much detail now. I'm not going to have time to do this, but all of these are parts of the Grampian group in the Central Highlands of Scotland, and they have been analysed for their zircon profiles. Yeah, and the Colonsay group looks a bit like this, the upper and the lower Colonsay group, and the argument runs from Claire McAteer's work is that it looks a bit like these things here, and so a correlation with the Grampian group is sort of indicated quite strongly by the zircon profile, although you couldn't rule out correlation with some of the Moyne. The problem is the Moyne was 700 kilometers away at the time, so this makes a lot more sense, and the geology of some of these Grampian group rocks is pretty similar. It's deltaics and fluvitiles and conglomerates, so the geology looks similar. This has only got one deformation, one major deformation. The Grampian group is deformed in the Grampian orogeny. So if the Colonsay group's only got one major deformation, apart from a later Silurian thing, then it makes sense that it's correlatable with the Grampian group. That seems to be the logic. And there's the Grampian group in central part of the Highlands, the Coriaric and sequences. There's the Bangor stuff, which is the basement to it. But we think these are bits of blue on this map, this BGS map. The bits of blue in Colonsay and the Isla are the same as this sort of khaki brown stuff here, and not that, not this, and nothing to do with the Torridonian. Although if you look at old maps, you'll find this is marked as Torridonian and that's marked as Lewisian. So we've debunked all that. We now say, no, this is Rins, it's very different to the Lewisian, and this stuff is probably Grampian group Dalradian, earliest part of the Dalradian. And there we are. I've just drawn this, pinched this out of the Geologist Scotland book, the Colonsay group here, and these are the Grampian group. Glenspeen, Coriaric, Glenshira subgroups, and the Colonsay group probably fits in here. Yeah. We know that the base of the Glenshira group is 804 because there's some dating of some pegmatites that it sits on here, and we know that this stuff here is older than that, and this stuff has only got one deformation. Yeah. So if the Colonsay group only has one significant deformation with the later one and later Silurian one, then the Colonsay group must be younger than 800 or in that area. And we know the Appin group, we know those who looked at the Askeg Tillite with me said we believe that's Sturtian at 720. So we've tightened up the group. We think it must be sort of between sort of 750 and 800 million years old. That's the sort of essence of the argument. Though it's tenuous because it's relying on correlation and plots and graphs, and it's not. We cannot date the Colonsay group directly. It'd be nice if we could, but we can't. And what was happening at the time, we believe that a lot of the sediment transport came from the west, and a lot of the rocks, the original zircons and stuff, came from places like Labrador and southern Greenland into this thing, which was the beginning of the splitting up of Rodinia at 800 to 750 million years, which eventually became the Apatus. But this is a rifting episode. And I tend to think that this is like the Perma-Trias of the northwest Europe, which is a precursor rifting and extensional stuff that happened before the South Atlantic got going. So it was a precursor. This Grampian group is a precursor to the true sort of rift and drift sequence that we see in the main Dalradian. The Grampian group was a sort of strange sort of beast of deposits in a sort of rift setting that was open to the ocean, because it's definitely got marine stuff in it. Quick look at the very last couple of slides. There's Colonsay. If you went offshore Colonsay and drilled a few holes, you get the old red sandstone lawn plateau lavas. They occur in boreholes just off there. There's the Loch Grignard fault trundling through here, and the Colonsay Basin on the other side of the Great Glen Fault with its Mesozoic fill. That's got Triassic, Cretaceous, Jurassic, Cretaceous stuff to the north. So we've got this little triangular wedge of the Dalradian stuck here. The later intrusions, there's some later intrusions in the Carboniferous. There's a Monchiquite, I can't pronounce it very well, but there's probably Carboniferous thing with an ethylene felspathoid weird rock that occurs here and here. It's 300 million years old probably, but there's one nice one at Kilchat, and then there's some and then unlike Isla and Jura, which have quite a lot of dikes in the Tertiary or the Paleocene dikes 60 million years ago, there's only just a few scattered around. They're not significant, so there's not a big story to be told here. This was outside of the main Blackstones Bank sort of Isla Jura swarm. That's why there's a few more on the south side, but virtually none on the north side of Colonsay. We do get this strange Carboniferous thing here, and it could be that's the same thing offset by these strike slip faults. Yeah. Could be. So thank you. Have a drink. Not on me. You can go to the pantry, wait for your ferry, lovely scones and tea, or you can get Colonsay gin. There's a lovely brewery on the island here near the ferry. So, yeah.
Wow. Thanks very much, David. That's amazing. So much geology in a small island, and so much detail you've taken us through there. I know some people have had to leave already, and they've been sending messages saying that thanks very much. Just a reminder that we've been recording this and we'll be putting it up on YouTube. We'll be doing that in the next couple of days, so you'll be able to have a look back over that and absorb some of it. Fascinating story, and just like the other islands we've seen, David's got this brilliant way of kind of getting us to the detail and the kind of key understanding of how it fits into the bigger picture as well. Really nice examples of interesting rocks to look at. So I'm sure there'll be a few questions, but if you need to get away, thanks for your company, and see you again soon, hopefully. Anyone get any questions? You should be able to unmute your microphone if you want to chat.
Yep. About the explosion places, what kind of depth, how do these relate to a volcano? There's no other signs of volcanic activity on which are exposed anyway. Would they be very deep, and you just got all the extrusive stuff is obviously totally and utterly gone?
Yeah, I mean, I don't know exactly how deep they would be. I mean, I can read some of the reports. I would have thought you're probably talking about a couple of kilometers, I would have guessed, something like that. Yeah, I mean, we've had uplift and denudation of the thing, so we are looking at the core of something here.
Yeah.
But I mean, those explosion ridges, I can't believe they're that deep. I mean, they must be fairly, I know, without looking at the reports and some of the papers on it, but there are papers. There's a paper on the explosion breccias further on the mainland that they're obviously the same age, and it'd be interesting. I'd be interested to look those up. I will Who's speaking, by the way?
Oh, there's Richard here, Richard Doak. It's certainly, we've stayed in Colonsay in a house, different houses there a couple of times, and certainly there's the explosion breccia there is a very, very obvious little feature and absolutely intriguing as to what on earth was going on there. But it's
yeah, I mean, certainly a lot of gas streaming. I think there's a lot of gas involved, not just fluids. It's a sort of gas streaming seems to be the key mechanism for emplacement and actually the breaking up. But it must have been very forceful. I mean, you couldn't break some of those rocks with a sledgehammer. So how they get smashed up like that, I don't know.
It's a little bit older than the Highland granites and Glencoe and stuff like that.
No, it's I mean, it's all Silurian. It's 430. It's Wenlockian. It's yeah.
And I always think it was a fascinating.
Dated. The cyanite there has been dated. Rod Muir had dated it. There's a 1997 paper by Rod Muir that dated it. There was quite an intrigue. I didn't go into the history of it, but there was an intriguing part. If you read some of the publications, this whole myth about this sort of conventional wisdom, shall I say, about the two deformations on Colonsay. If you go back to 1907, there's a paper written then called "The Two Great Earth Movements of Colonsay," and the original dating that was done on the cyanite at Kaloran by I think it's Mark Bentley in 1980-ish, mid-80s, dated it at 600. Yeah. And that was, wow, that means that, and he thought that there was post 600 deformation and pre 600 deformation, and it was intruded in between the deformation events. So this paper was written about the 600 million year old thing and it sort of led weight to the whole concept that Colonsay had two deformations separated by a 600 million year old intrusion. And therefore that pushed people into thinking it was older rock. This was much older, that it was about 800, 900, maybe 1,000, correlated with the Moyne. Maybe it was a fallen basin to the Grenville orogeny. So there's all sorts of stuff in the literature about that now. It's quite possible that these are derived from or if they are 800, that they're derived in an orogenic, from the erosion of the orogenic cycle that affected the Moyne, the Rhinelandian, Neudatian orogeny that affected then, which is dated around at about 850 to 700 and 800-ish. So there was obviously a mountain belt being eroded into it. But the dating of the Kaloran cyanite was an interesting story geologically.
Could I ask a question, David? Zircons in the gneisses. It's one thing to have detrital zircons and date the youngest age, therefore, that they represent. But what about them in the highly metamorphosed stuff at the beginning? Are we sure they were formed with that metamorphism, or could they have come in be formed much earlier?
Well, the idea, the concept is that they are representing the magmatic cooling of the zircon. Yeah,
it has a decomposition temperature. I'm just noting. I've looked it up, of about 1500. So
yeah, I mean the work that Steve Daly and co have done on these things looks very good to me. So I mean, I would suggest that they are looking at a cooling age. These are true cooling ages. They are zoned, and they have rims, and they have discordant data, and they have lead loss, but they can correct for that. These are, if you look at all the Discordia, Concordia plots in the literature, it looks pretty rigorous to me that they are looking at a true cooling age for the granodiorite, and they're very convinced that it's older and more juvenile crust than the Rins stuff at Isla, which is sort of 100 million years younger and more evolved.
Right. Yeah.
Read the papers, they're great. I mean, they're really into metamorphic zircons and igneous, and the whole isotope chemistry of these rare earth stuffs, the hafnium isotopes and the samarium neodymium dating. Brilliant stuff if you're into geochemistry.
Yes, I must have a look. Yeah.
So the papers are there. I mean, it's I can if you can't find them, let me know. I can get copies to you. You know?
Yep, we'll try and have a look. Thank you.
David, it's Nick Pierpoint here. I just had a question on the cyanites at Cooleran Bay, they seemed ever so variable. You had pictures where it was quite pink, and yet not very far away there was a very mafic rich example. Are they in contact with one another? Were they part of the same rock?
It seemed to be. Yeah, this seemed to be that example I showed you. It seemed to grade from a almost entirely feldspar rock to something that was 50% mafic. So I don't understand the differentiation process that's going on there and how it's got there. I must admit, I'm not an igneous petrologist, but you don't find many cyanites and diorites in the oil fields. But
if you do, you're in trouble.
But yeah, I mean, there is a paper on it. Rod Muir, 1997. They did the dating on it and came up with the 430 rock and some of the survey, the original Cunningham, Craig and Battersby Bailey stuff from the very early part of the 20th century is brilliant descriptions of this stuff. So you can have a read of that. But you're right, it did look a gradational thing. I mean, when I first went there, I thought, oh, pink cyanite, then there's the hornblendite with the quartzite pebbles class in it, and then there's the explosion breccia with that. So there's three things. Then I looked at some of my pictures and my notes, and I thought, yeah, there is a gradation between the pink and is the dark mafic cyanite is that part of the hornblendite? How does it relate? Then you find that the exposure is there's a lovely rock in the sand, and then there's sand, so you can't see, and then next time you go there, the sand's moved and it's all changed again, and you can't see the same rocks again. So,
and I guess the other thing,
then it's worth it.
And just another observation as you move through describing the explosion breccia. The first photograph you had, there was quite angular fragments there, but there didn't seem to be much fine-grained material. Was that right?
No, it all seems. You're right. I mean, they're very angular and packed together, but there's not much smaller stuff. It all seems to be quite chunky. I hesitate to call it well sorted because it's sort of a bit sedimentological, but you know what I mean.
But that was probably the case because it was such a violent. Event.
And it's got to be to do with buoyancy and the way these things must have all been suspended in a gas cloud, in the gas stream. It must have been a phenomenal thing.
Yeah.
That explains it's gas. It explains why there's very little matrix to it, and these things must have, and then to pack it in and pack it in like a jigsaw with virtually no matrix. And did it soften them? Did it? I don't know. I don't know about the rheology of the thing. What's going on?
To weld them together.
They're almost welded together. You're right. Yeah. So they'll be. Yeah.
Well, should we let David go away and get a dram? Sorry, we can't pour it for you.
Very well deserved.
It was fascinating. Thank you.
It's a lovely little island. I say you just look at a map and you think, well, what's that? But it's a geologist's dream, and the fact that if you go to holiday to Islay, just go to Colonsay for a day and just potter around. But it's beautiful.
We spent a week there and we had the worst weather you could imagine. So trying to encourage my wife to go back there again, it's going to be tough work.
Yeah, it does sound like the geology is enough to certainly occupy you for a good few days, doesn't it? It's amazing. Yeah, I love these little islands that get such a rich story, even if it's mainly the one from the one part of the sequence. But actually, there's a lot to it. So I think you've done us proud tonight, there. Thank you for a brilliant introduction, and I think we'll close there. Thanks
thank you
for your company. Thanks for the series over the last few weeks, David. Really nicely done, and really great to have recorded them as well and put them online so people can go back to them and see them.
Yeah, thank you very much, guys.
Thank you.
Okay.
Thank you.
Good night. Thanks very much.
Bye now.
Thank you.
Bye.
So we should be able to get his, because it sounds so